Okay, let's start the lecture today. So, as you know, we are uh, discussing this topic of Ranjay Katha methods, okay, which is chapter 25. So, in this topic, last time we have already discussed the Euler's method and some variations in the Euler's method with the uh, decrease of the step size as well. So we have discussed the Euler's method, and today we are going to discuss about some improvements into the Euler's method. Okay, so I did not follow this uh, PowerPoint slide last time, but uh, we can go through that whatever we have covered over here. Yeah, so we have covered up to this point. So now we are going to start with the improvements of the Euler's method. Okay, so a fundamental source of error in the Euler's method is that the derivative at the beginning of the interval is assumed to apply across the entire interval. So as you can see that the derivative of the function across the entire interval is in reality does not remain same, but we assume in this method. So therefore, this is the source of error in the Euler's method. So in order to improve on this source of error, we can make some changes. We can say make some changes into the uh, Euler's method, some modifications. And there are two types of modifications which we can consider. The first type of modification is named after Heinz. So it is called as the Heinz method. And the second modification has the generic name, which is called as the midpoint method or improved polygon method. So in Heinz method, to improve the estimate of the slope, it involves the determination of the two derivatives for the interval at the initial point and at the end point. So you determine the derivative at 2 points. So just imagine that in the Euler's method, we have this function, okay, derivative function. So we just take the, uh, we find the value of the derivative at the initial point, okay. But in the Heinz method, to improve on that, we use the initial point derivative and we use the initial point derivative, and then with as a result we can using that initial point derivative you can predict the value of the function at the next point by using the Euler's method. However, that prediction of the value of the function at the next point is used to further correct it by using the same value for the next equation. So in this way, then we can get two derivatives, okay, and then we can obtain an improved value of the function. So we can use these two equations, okay. So this is how the Heinz method works. So we first find the predictor. So that means we use this value of the slope to find the value of the y at the new point. But using this value of the y and using the same original equation, we find the new slope. So then we take the average of these two slopes. Then we take the average of these two slopes, and this gives us the value of the function. So this method is also called as the predictor corrector method. So we predict, and then we make corrections in our prediction. Make corrections in our prediction. In this case, if you will see that we predict the value y I plus 1, that is for the next interval, and then this predicted value is again corrected, which is again yi plus 1, I plus 1. We have just differentiated them with some the predictor with the superscript 0. Otherwise, both are the uh, forecasted values of the y. In this case, the forecasted value of the y in the second equation and the forecasted value of the y is also available in the both sides of the equation. So it means that we can use this equation iteratively to improve the value of yi plus 1. Okay, so we can predict it for the first time, and then we can iteratively improve it, the corrector value over here. So this is the graphical depiction of the Hines method. So you calculate yi plus 1. So from yi plus 1, you calculate the average, and then again yi plus 1. So this is a kind of a loopy method. Then we can stop at certain point in the loop when we get the desired level of accuracy or precision. Okay, so let's see this Hines method with the help of this example. So the example of Hines method is example this one, example 25.5. Okay, so the example 25.5. So use Hines method to integrate dy over dx, that is y prime, is equal to 4e power 4 exponent 0.8x minus 0.5y from x is equal to 0 to x is equal to 4 with a step size of 1. The initial condition at x is equal to 0 is y is equal to 2. Okay, so if you see that this is a first order linear equation from the course from your course in a differential equation. You have solved these kinds of equations, first order differential equation. And if you see that this is the first order linear differential equation, if you apply the method of the integrating coefficient on both sides, then we can find that its exact solution is this, y is equal to 4 over 1.3. Okay, so from your knowledge of the differential equation, we can find its exact solution. However, in this course, we are we are interested with the numerical solution. So we can use this exact solution, but we can also find the numerical solution, and we can compare the numerical solution with the values obtained from the exact solution. Okay, so in order to apply the Hines method, remember that what is the Hines method? In the Hines method, we take the average of the two slopes. Okay, so this is the main point. And we first take this value of x, which is 0. Okay, and taking this value of x and of course y is equal to 2, we input these values into this equation. X is equal to 0, y is equal to 2. These are the initial conditions given. So with this, we can find the predicted value of y, which is equal to 3. Okay, so this predicted value of y, which is equal to 3, is now used to obtain the new predicted value by the Euler's method. So this is actually the slope. So first we find the initial slope. 3 is the initial slope. Then we use the simple Euler's method, which we tried before, to find the predictor value of y, which is equal to 5. Okay, so 3 we use in here. 1 is the interval step size. Yeah, step size is 1. So first we found, in this case, we have found the value of the function of y at x is equal to from 0 to 4. So the next value will be at y x is equal to 1. So y1 is equal to this. And then we will use this new value of y, which is 5, into this original equation to find the value of the new slope. So this will be the new slope. So remember that initial slope was 3, new slope is 6.402. We can take the average of these slopes, and then we can use the average of these slopes and then apply the Euler method again, okay, to find the corrected value of y, okay. So therefore, in this case, as you can see, this Heinz method is the iteration, okay, iteration includes these steps. First, find the initial slope, okay, find the initial slope, use the initial slope to find predicted value, okay, and use the predicted value to find the initial, and the second slope, we can say initial final slope, okay, final slope, okay, use the predicted value to find the final slope. So average the initial slope and final slope, okay, average the initial and the final slope, and use the average slope to find the corrected value. Yeah. So these are the steps, okay. So this is the typical iteration in the Heinz method. So these are the steps, okay, which you will take. Okay, find the initial slope, use the initial slope to find the predicted value. So how you will find the initial slope? You will use the differential equation, a given differential equation, okay. How you will find the predicted value? Use the simple Euler method, okay, and use the predicted value to find the final slope. So it's again use the given differential equation, but in this case you will use the new value, predicted value in place of y, okay, and then average you can, you know how you can find the average, okay, and use the average slope to find, and then in this case use the simple Euler's method, okay, use the Euler's method. So use the Euler's method, okay, simple or just Euler's method. So in this way the steps will continue. Okay. However, we can further improve. We can further improve the corrected value iteratively. Okay, you can further improve the corrected value iteratively. That is, this value which we have found, we can further improve iteratively. Okay, by the repeated use of this step 5. Okay, by the repeated use of step 5. So this has actually been done in this example, okay, example 25.2. Okay, so let's apply this example so that it becomes more clear. Let's do this hands-on approach to do this example using Excel. In fact, I have already done it for my practice, but let me repeat by doing it again in this new sheet. Okay, so this is the problem situation, and this is the given equation, and then I will not go back to the our original course to derive it, but I expect that you can do it by the method of the uh, integrating coefficients to find its exact solution. Okay, so this is the exact solution of this given differential equation. This is the exact solution of the given differential equation. So can you see this Excel over here?
Yes.
Okay, so for this Heinz method, we have h is equal to 1 in this case. So we are taking a step size of 1. We are starting from x is equal to 0. And then for x is equal to 0, y given y is 2. Okay, so what is the first step in this case? The first step is the find the initial slope, use the given differential equation, okay, using the given differential. So we have to find the initial slope. So the initial slope, okay. So we have to find the initial slope. Okay, so yeah, initial slope. Initial slope is now we can find the initial slope by using this equation. Okay, so for this equation we have the value 4 multiplied by exponent function 0.8 times x and minus 0.5 times y. Okay, so this is the value of the initial slope. And then what is the next step? Next step is the use the initial slope to find the predicted value by the Euler's method. Okay, so for the Euler's method, remember that what is the formula for the Euler's method? And so we can always go back to look at the formula for the Euler's method. Okay, Euler's method is where is the Euler's method? Yeah, this is the formula for the Euler's method. So I can input this formula over here as well. So now you have to use this value to find the value of uh, new y. Okay. So what is this predicted value? Okay, predicted value. So the predicted value is equal to the value of y. The value of y was this 2 before plus slope. So this represents the slope in this case. Okay, this represents the slope. So 3 times the h, which is step. So this is this. So I don't want to change this value of the step, so I take it as constant. So this is the predicted value, predicted value of 5. Okay, so the next step is use the predicted value to find the final slope. So now we have to find the final slope. So for this again, so now I will use this value of y to find the final slope. Okay. So the final slope will be at the new value of x, okay? At the new value of x, okay? So predicted value, and then we can say that the also we can see that the value new x. Okay, so for this we need the new x value. Okay, so the new x value is equal to the previous value plus the step size. Okay, so using these new x and new y values, we can find the new slope values. Okay, new slope value. So that is the final slope. Okay, final slope. So final slope will be equal to this new x value, that is equal to 4 times exponent. Okay, 4 times exponent is 0.8 times this new value of x minus 0.5 times new value of y. Okay, so this is the new value, 6.402164. Okay, and let me check. Oh, this was yeah. So was this correct? 6.4. Yeah, 6.402. Okay, and then we have found the predicted value of the phi, and now you will use this predicted value use the predicted value to find the final slope. Now our next step is to find the average slope. Okay, average slope. So average slope is equal to the slope before. What was the slope before? It was this. And what is the slope now? It is this, and then divided by 2. So it is 4.708. And now is the corrected value. So the corrected value will be used by the application of the Euler's method. So corrected value is equal to the initial value. So initial value is this y. Okay, initial value is this y. Okay, and then plus the average slope is this multiplied by the step size, which is this one. Okay, remember that the initial value of y you will take from here, not from here, because we are going from first step to the second step. So the first step is over here. Okay, so this will give us this value 6.701085. Okay, which is the same as this. Okay, so in this case now what we can do is now I think we have already set up this equation, and then we can go from x is equal to 0 to x is equal to 4 by simple copy and paste to this. But I think for this I need to increment it. Okay, so our next step will be is equal to this plus h. So it should be 1. So this is the corrected value. Okay, so now I can just copy it down, and yes, so I get these values 6.701. Yeah, so I just compared my answers with this over here. Where is this? Yeah, 6.701, 16.31, 16.31. Yeah, I get 6. Oh no, here I am getting now 14.00. I'm not getting the correct answers over here.
You have to change y. It's
I have
from
to
2 it
change y.
goes to, yes, it's not 3,
Yeah.
I guess.
So I have to change y, right? So yeah, so what value of y I have to change? So I have to change it equal to this predicted value. Yeah, I think so. Yes. So now it should work. Okay. So what I am getting is what values I am getting now. So this is the value. So okay, this value I got for x is equal to 1. Actually, I have just a little bit. So this is the value at x is equal to 1. Okay, this is 2. This is 3. This is 4. Okay. So 6.7, 16.31. So 16.31, right? 37.19, and it is 37.19, and 83.33, it is 83.33. Okay, so here I have got these values. And then of course this we don't need this step. Okay, so we can say that this is the value of x. So in this way, then we can apply this Hines method step by step. So just remember these steps conceptually, and then we can find it. So it is also said that we can improve this corrected value iteratively by the repeated use of step 5. Okay, here you can see that these values have been provided in this example. Okay, these are for the values of predicted values of x, 2, 3, and 4. For the case of x is equal to 1, for example, this value of 6.7 can be repeatedly applied to improve it to 6.36, to improve it to 6.36. And this is with the help of this repeated application of this equation. Okay. So how we can improve it? So maybe what I can do is I can take this value, okay, and then I can improve it. Okay. So how I can improve it? So let me show you this predictor corrector equations as well. Yeah. So predictor corrector equations I can use. Okay, so we have these predictor corrector equations. Okay, so how we can improve this is iteratively. So we have the value of y is equal to this value. Okay, so here we can apply the iteration. Okay, and then the y for each y per iteration. Okay, so first iteration, then we have second iteration, and then we can go up to as many iterations as we like. So for the first iteration, the value of x y is this, which was calculated 6.70182. So for the second iteration, this should improve. But how we can improve? We can apply this second equation. Okay, this second equation. So how we can apply the second equation is equal to yi. So this is the because this is we are finding it for the first value. So the our initial yi will be this given value 2. Okay, that will be the given value 2, and plus. So plus, now we have to take this average. Okay, take the average fxi yi. So which is equal to, which is also constant. Fxi yi we already calculated by this. Okay, this value. This will be constant. The only thing that will change, that will be fxi yi plus 1. But that we will, just since this will change, so we will calculate it with the help of the Euler's method. Okay, so it will be then by the Euler's method, then it will be no, sorry. This will be, since this will be the slope. Okay, slope. Okay, so this slope we will calculate by this method. Okay, so it will be 4 times exponent of 0.8 times the value of x. The value of x will be this. In this case, the value of x will be equal to 1. And then plus, minus 0.5 times the value of y. The value of y will be the because will be the new predicted value. So what will be the new predicted value? This previous value. Okay, this is the only thing that will change. So in this way, this value is giving us the slope. Okay, so actually I am just making some. So this is the 0.8 times 1. This is the exponent minus 0.5, and then this one. Okay, and then divided by 2, and then multiplied by the h. H is actually just 1 over here. And that's all. So this will now go to 6.27, and now I can just copy it down, and then I can see that after some iterations, the value will be converging to 6.360865. So 6.360865, which is the same value which was obtained over here. So similarly, for each of these x values, we can find these different values after the 15th iteration. So as you can see that, so we first found the value of the corrected value by the first iteration, and then we can further improve it by the repeated applications of this equation. And the improvement has only used this new changing value of y. So that means each time we are using the previous value of y, we are doing it iteratively. Okay, so in this case, we can use the predictor corrector equation to find the values of the new function by this method, Heinz method. Okay, is it clear?
Yes.
Okay, so this was the Heinz method. So remember this 5-step methodology for this Heinz method. And and now the next improvement was, if I go back to the PowerPoint slide, the next improvement was the midpoint method or the improved polygon method. So in the midpoint method is the use Euler's method to predict a value of y at the midpoint of the interval. Okay, so this value is substituted into the ordinary differential equation to generate an improved slope, which is then used to project from the beginning to the end of the interval. Okay, so here in this case, first what you do is you have the value of x and the value of the interval. So at half the interval, you find the new slope. Okay, at half the interval, you find the new slope, and then use this slope with the initial point to find the value of x. So this is relatively simple. It involves relatively a few number of steps than the previous method. Okay, so in this case, for the midpoint method, that means for the midpoint method, the number of steps for the typical iteration are so for find the slope. Okay, find slope at midpoint. Okay, find slope at midpoint and use the slope, use the midpoint slope at the given point. That means at the beginning of the given point, at the given point, to find the value. Okay. So it has only two steps. It has only two steps. So find the slope at the midpoints, use the midpoint slope at the given value. So in this case, if we want to apply it, so for example, for the same method, so this is the midpoint method. So I take the same x and then y values. So x is 0, y is equal to 2. These are the initial values given. So what will be the first step? Find the slope at the midpoint. Okay. So midpoint slope. Okay. Midpoint slope. Okay. So what will be the midpoint slope? So midpoint slope will be the slope will be given by the this dy over dx equation, and since the our point is 0, the next point is at 1, so the midpoint will be between 0 and 1. Okay, so midpoint slope will be at 0 and at 0.5. Okay, so find the midpoint slope. So the midpoint slope we can find. Okay, just we can take one more step, is that we need a midpoint. So midpoint is equal to this value plus 0.5 times the interval. Interval was this. Okay, so this is the midpoint, and midpoint slope will be equal to 4 times exponent 0.8 times this value of the midpoint minus 0.5 times the value of y, which is this. So it is 4.9672. Okay, so we get this slope, and then therefore this midpoint slope will give us the value of y. Okay, so that means the so use this midpoint slope at the given point to find the value of function. So function value, that means our answer So our answer, the function value. Okay, function value will be then equal to, now you will use this function value, and that, what we will use the Euler's method. Okay, this Euler's method to find the function value. So, and then that will be equal to yi is equal to 2 plus the slope, which is this, and times the value of h is here. So in this case, we will get a value of 6.96. Okay, 6.967. However, in this case, we cannot improve this. We cannot improve it by these repeated calculations. So, in fact, in this case, we can see that the errors for the midpoint method, the error is slightly more, but it can be more or less depending on the value of the function as well. And one more thing is that we can compare, because we have the original solution over here, so we can compare this these calculated values with the original solution values as well. So to find the percentage error. Okay, so here, as it has been done in this 25.5 example. The percentage error. So because in this case we have the true solution available, so we can find the values of y, and then we can compare from the true values of y and the predicted values of y, we can find the percentage solution as well. So this is how we apply the Heinz method and the midpoint method. Okay, so now let's move to the more journal type class of methodologies, which are called as the Runge-Kutta methods. Okay. So do you have now any question about the Euler's method and its improvement?
No.
Yeah. Okay. So yeah, so now we are going to discuss about the Runge-Kutta method. So Runge-Kutta methods are are more accurate than the Euler's method, and their improvements as well. In fact, all the Euler's method and their two improvements are some cases of the Runge-Kutta methods. Okay, so Runge-Kutta methods are the more generalized forms of the numerical solutions of the differential equations. So that's why the name of this chapter was also called as the Runge-Kutta methods. Okay, so Euler's method and the two improvements in the Euler's methods are the special cases of the Runge-Kutta methods. So in the Runge-Kutta methods, we have the solution of the differential equation in this form: yi plus 1 is equal to yi plus phi xi yih. Maybe I can go back to this PowerPoint. Okay, so this is the midpoint or the improved polygon method, which we just considered. So Runge-Kutta methods achieve the accuracy of a Taylor series approach without requiring the calculation of higher derivatives. So as I have just actually told, that Runge-Kutta methods are the more generalized forms of the numerical solution of the differential equations. In fact, Runge-Kutta methods are derived from the Taylor series. Remember, the Taylor series is very useful, and which we also discussed it in chapter number 4. Every function which can be differentiated, which has the derivative, higher derivatives, can be written into the form of a Taylor series. So using the Taylor series, this Runge-Kutta methods can be derived. In fact, we will not go into the detailed derivation of the Runge-Kutta methods, but we can see two derivations which are given for the Runge-Kutta methods in the book for your on reading. So here I will only explain what the Ranjakata method is. So the Ranjakata methods is, or in short, we can also call them as the RK methods, can produce the solution in this form. So yi plus 1 is equal to yi plus phi x y h into h. So you can see that this equation is very much similar to the equation in the Euler's method. However, because in the Euler's method we have this function xy, but here we have this another function which is called as the phi, and it is called as the increment function. And this increment function is not just the function of x and y, it is also the function of this interval h. Oh, it is also the function of this interval h. And this function can be represented as this in the form of a polynomial or linear equation. It is a1 k1 plus a2 k2. So where a and k are some of the constants and the coefficients. Okay, in this case, a are the constants. So that constants we can determine later on. Whereas k1, k2, and k are functions. Okay, so k1, k2 are kn are not the constant; they are functions. So, and for each type of Ranjakata methods, we have actually first order, second order, third order, and the most common Ranjakata method is the fourth order Ranjakata methods. Different order of the Ranjakata methods depending on this value of n. We can define these functions k1, k2, and k3 like this. So if it starts from k1, so k1 will be the function xi yi. So which is basically the given differential equation. Okay, the given differential equation in the form dy over dx. Okay, so the value at the initial values of x, y. So this is fine, no problem. No, this we can find very easily. Now for the other k2, k3, k2, k3, and kn, we need to we can derive that k2 will be a function of xi plus p1h and yi plus q11 k1h. That means we can use the same first order differential equation. We can say use the same first order differential equations, but we can evaluate it at different values of x and y. So the different value of x and y will be incremented by p1h, x will be incremented by p1h, where p1 is another coefficient, okay, and h of course is the interval, and then y will be incremented by q11 or k1h. And here remember that k1 was previously calculated and q11 is a new coefficient. q11 is a new coefficient, and later on we will see that how we can find the values of p, q, etc. And similarly for k3, if we see that k3 will be incremented by p3h, okay, compared from xi, k3 will be incremented by p3h. So from p1 to I think there should be some, I think it should be p2, k4, and then yeah, it should be p2h. So there is this typing error, so it will be p2h, okay, and then y will be incremented by q21h and q22h. So for the case of y, there will be an increase in the number of terms. Okay, q11 times k1, it will be q21 times k1, and then q22 times k2. And you can see that these are the incremental, these k1, k2, and k3 are incrementally calculated, because for the calculation of k3, we have used k2. For the calculation of k2, we have used k1, etc. And then in this way, this process will continue. The advantage of Runge-Kutta method is that it is the higher order Runge-Kutta methods, such as third and fourth order Runge-Kutta methods, are very accurate, have much accurate than the Euler's method and their modifications. And the second advantage of Runge-Kutta methods is that we don't have to calculate the higher order derivatives. Okay, so we just have to calculate the initial equation and initial differential equation, and then we can find the values of these coefficients. Okay, so this was some brief introduction with the Runge-Kutta methods. We will continue this topic in our next 2 lectures. Okay, and
I
then
have a
hopefully
question.
we will complete it. Yes.
So, because the coefficients in the Runge-Kutta method are calculated sequentially, like K1, then K2, then K3, doesn't it mean
Yes.
that